Hello, everyone. Welcome back to the AAS Journal Author Series. And I am super happy to have Ollie Liu with us today. Hi, Ollie.
Hi, Frank. How are you?
Doing well, all things considered in the current epoch. Arizona is sort of a hot spot these days for the pandemic. So we sort of opened up a little too early and now we're kind of shutting down again, but we're doing okay. I'm doing okay personally. So how are you? How are things with the pandemic over where you're at? Where are you at?
I'm now in Beijing. I'm working for the National Astronomical Observatory of China. We are now start working.
Oh, you are? Okay.
Yeah.
So are things generally opened up? Or do you have things like restaurants open and stores open and stuff like that?
Yes, everywhere is open now.
Wow, that's pretty good. Great. Excellent. I hope we get there soon.
Hope so.
Very cool. So what do you like to do for research, Ollie?
Firstly, I will introduce myself. I'm Ali Liu. My name is Ali Liu, and I'm working on low mass stars recently.
Mm-hmm.
Yes, I will introduce a paper published last year about the M-subdwarfs because low mass stars are most dominated our galaxies.
Mm-hmm.
Our galaxy, but the previous works searched a lot of M-subdwarfs in the halo.
Mm-hmm.
For us, we have a telescope in China named LAMOST.
Yep.
The main survey, it's also a survey telescope, and the main survey, one main survey is the anti-galactic center, the direction, the disk. So we want to know how many disk subdwarfs can be obtained. That's the motivation of our work. Yeah.
Cool. So speaking of, why don't we get to it? And so this lovely paper, M-subdwarf research, 1, identification, modified classification system, and sample construction. And Ollie, take us away.
Yes, this is our first paper of a series. And now we have completed another one and plan to submit it in this week, just in this week, about the parameters and the kinematics analysis of these M-subdwarfs. So this paper, M-subdwarf Research 1, is an identification and modified classification system and samples. So just as I said, the motivation is to look for how many M-subdwarfs we can get from the disk, and the thin disk, and also we know that the M-subdwarfs are defined as metal pool stars.
Mm-hmm.
Most of them come from the halo. So they keep the same kinematics with halo stars. Mm-hmm. They don't have the same kinematics with local stars. Yeah. So in this paper we just use the spectroscopic method to get the M-subdwarfs.
Okay.
Yeah. So firstly, I would like to introduce the LAMOST footprint, the figure 1.
Figure 1. Okay.
Yeah.
Got my coffee in my hand here. Let's slide down to, okay, let's blow this up a little bit.
Yes, this is a figure 1, yeah. We can see that this is a footprint of Lamost survey, the DR4. The blue points here are Sloan's survey, Sloan's SDSS survey, which get a lot of subdwarfs, M-subdwarfs.
Mm-hmm.
All these are, and the red ones are Lamost observed. We got the M-dwarfs. You can see this line is the equator,
mm-hmm.
and you know, here in this region, in the center of this plot, this is the anti-galactic center direction. So we got a lot of M-subdwarfs around these regions. Why we, so to search for the M-subdwarfs, we use a traditional method developed firstly by John Jesus in 1997, and then revised by Lapin in 2007. But after we check, we find that Lapin rejected the calcium hydrase 1 as a criteria by Jesus. Lapin just used calcium hydrase 2 and 3, okay, versus titanium oxide. Please check see the figure 3.
Sure. Figure 3. So there's the features used in the classification. You can see the calcium and TI.
Oh, please wait. Here is a figure 2. I will introduce something about the figure 2. Figure 2 is an example of the M-subdwarfs. You can see the most important features are calcium hydrase 1, calcium hydrase 2, 3, and titanium oxide 5. For the normal M-dwarfs, okay, the feature titanium oxide should be deeper, a deeper one. So it's very easy to check star if it's a M-dwarf or M-subdwarf. Just compare this calcium depth and the titanium, right? Because it's very easier for people to use eye checks. But for a large quantity of data, we cannot do this by eyes. Too many of spectra. So please go to the figure 3.
Certainly. Okay.
This figure on the left one, this figure is all the all the points in the figure are the Savacheva's work on Sloan's in 2014. This work, she got around 3,000 M-subdwarfs from Sloan's data and all this. We can see she used Lapin's criteria for separating M-dwarfs and M-subdwarfs. Okay. But when we see when we use calcium hydrase 1 and the titanium oxide 5, we can see part of them have been misclassified as subdwarfs. Actually are M-dwarfs, not subdwarfs.
Yeah. Okay.
So we have to get these criteria back. Both this criteria and the criteria used by Lapin's. So that's
Yeah, you got to You got a nice dark line there representing equation 2. So I just want to slide up and remind myself what equation 2 is. Equation 2. There we go. Let's put it all on. Okay. So it's a relation.
Yes, equation 2. Yeah, just describe these lines.
Okay.
Yeah.
Okay. Very good. Okay.
Yeah. So then we have to revise the. Also, we have to revise Lapin's criteria about the calcium 2 and 3, and check if it's adaptable to Lamost, because the instrument is different. So the line indices may be different. So we have to check that. So we use some. I checked labeled M-subdwarfs and combined both with some dwarfs. This work, for this work we make a lot of time. We spend a lot of time to do that. We checked around 10,000 spectra actually. Eyes by eyes. That's a hard work. Totally for about half a year. 2 people to do that. We spend half, and to check one by one. That's because previously we have published some subdwarfs, M-subdwarfs in Lamost DR2. We have some experience to do that. In that work, we have only around 100 M-subdwarfs published, but the criteria is very strict. So now after that we we use DR4 data, just the 4th year, not the whole DR4, just 1 year data to get the M-subdwarfs by eyes.
Do you think maybe going forward, or as a check, using some sort of an automated?
No. In that step, we just use. We want to make a good sample to study the Lapin's criteria. So at that step, we checked one by one by eyes to check the spectrum to measure the line index by eyes, not quantitatively, just by eyes to check. Okay, I think this is M-dwarf and that one is M-subdwarfs, something like that. And then we got a very good sample, about 400 labeled subdwarfs and more than 80,000 M-dwarfs, normal dwarfs, 80,000, more than 80,000. Because we need to, we need another factor. We need to, because we want to measure the line indices precisely. So another point is to to move the spectrum to the rest frame. The radial velocity is a key factor. Yeah. So all these labeled M-subdwarfs and M-dwarfs are have been measured good radial velocities. So yeah, and by this, and we recalculate the line indices actually. Yeah. Here I want to say some words about the radial velocities. In Savacheva's work in 2004, she this in figure 3, all these points in figure 3 are subdwarfs from Sloan's. But the line indices, she measured not to use her own radial velocities. She used the West. She used the radial velocity from the West catalog.
Okay.
That catalog is the M-subdwarf catalog. So she measured the radial velocity using the M-subdwarf template to get. So there are some errors about the radial velocities. Then using that radial velocities, they get the not very precise line indices.
Mm-hmm.
So that's why here are some problems, maybe not all from the criteria of the calcium hydrates, but some of them are caused by the radial velocities, the measurement of the calcium 2 and the calcium hydrates 2 and 3. Yeah.
Right.
Yeah. Right. So let's go to the figure 4. Yes, figure 4.
Sure. There's your problems there. Okay, figure 4, sensitivities.
Yeah, yes. Sensitivities of the spectral classification, yes. From this figure, you can see, yes, there are the classification of M-subdwarfs, because in the beginning, in 1997, John Jesus used just use the calcium hydrates 1 and calcium hydrates 2 to classify the subdwarfs to M-subdwarfs, M-dwarfs, M-subdwarfs, and extremely M-subdwarfs. And the Lapin get another one, ultra subdwarf, ultra one, use this line. Yes, use this line. So that's a good criteria. It's a good one, and they defined metallicity index called zeta. That means the ratio of calcium hydrates and titanium oxide.
Okay.
Yeah.
Okay.
And we checked use Lamos data and revise this revise these criteria. Just using the same equation, but the coefficients are changed because using our criteria.
Right. So you pick up a whole bunch with zeta around 1.
Yes.
Mm-hmm.
Yeah. And yeah. For the in this picture, you can see the criteria for the ultra hydrates, and this is yeah, they use just like the zeta greater than 0.8 is a criteria for just to classify the M-dwarfs and the M-subdwarfs.
Okay.
Yeah, but in ours we have revised this and get. Let's see the picture. Figure 7.
We will slide to figure 7. Render, and render some more.
Yeah.
Load up.
Yeah, this is revised lines. You can see there are different lines here, and you can see these black lines. These black lines are our our criteria. This one is cut. The left one is a cut for the dwarf, normal dwarf, and the subdwarfs.
Okay.
All our select, most of, not all, most of our targets are classified as M-subdwarfs using this criteria. And yeah, it's better. And then we got more than, 2000. This picture is just to get the criteria. So this red targets are labeled M dwarfs. The blue ones are labeled M dwarfs. This one M subdwarfs.
Right. Cool.
So yeah, we are using this revised criteria combined with the calcium 1 and calcium 1 versus titanium oxide. We checked all the 1 million, more than 1 million spectra from Lamos DR4. So from the more than 1 million spectra, finally we got around 10,000 candidates, and then we checked one by one by eyes. Another time, to get totally, we got 2,800 around M subdwarfs.
Got a 1%. Okay. Yield harvest.
Yeah. So we actually, in this work, we did not use the Gaia data. When we finished this work, we checked the Gaia data, and we find that not all the M-subdwarfs we got located below the main sequence.
Okay.
Not all. Some of them are located just along the main sequence. So in the next paper, in the following one, we checked with the kinematics and also the metallicities. The metallicity defined in this paper, the paper 1 is just use the zeta metallicity index, not real metallicity.
Yes, understood.
Because the line index is not affected only by one parameter metallicity. They are, for example, calcium hydrates 1 are also affected by the gravity and so on. So in the following work, we are checking about the metallicity. We use phonics model to check the behavior of the spectra with the parameters. We got a very good relations between them, and we feed the spectra to the templates, and then we got very precise parameters of these subdwarfs. And we also have the kinematics, have the parsec, and have the proper motions from Gaia. So we got very good data. And then we find that some of these M subdwarfs should be metal pool dwarf, not subdwarf.
Okay.
So in the following paper in this week, we will submit the new studies of the subdwarf. That's paper 2.
Cool.
Yeah. So it's a very long paper, but I'm now cutting. I'm now working on cutting the lot of the things, not necessary parts. So that's work.
Good.
So yeah.
Do you anticipate that one being a supplement? Are you going to aim for APJ supplement, or is it more of a main journal article?
Journal article, I think, because we don't need to give the catalog. We just give the analysis and some physical analysis of this. So I think it's better to submit to the journal article.
Okay, cool. So we're done with this one? Because we're already on paper 2. Okay, very good. So that's paper 2. So you're about ready to go. If you look in your crystal ball, where the field goes as we look for these subdwarfs, is there going to be a paper 3 in this series? Where does the field go in the next, let's say, 5 years?
Because I think right now we have only get a very small part of spectroscopic observation of the M-subdwarfs, because it's intrinsic low luminosity. It's not easy to get the spectros, but we want to know. We want to get some relationship between the photometric and the spectroscopy. We just make the, we want to generalize the spectroscopic method to the photometric method to get more. Right. And this maybe use the machine learning method. We want to use the deep learning and something to find some maps of the spectral features and the photometry. Actually, of course, they use not only focused on the optical, just many of them is the near infrared or infrared. Mm-hmm. So we have to make a lot of study on that. And then we want to get more because because a lot of, I think maybe the magnitude, if we can get the magnitude to 25.
Okay.
If we can get that, we will get a lot of M-dwarfs and the subdwarfs and even some brown dwarfs. Actually, the brown dwarfs is not easy to find in Lammas because it's too faint for Lammas. The Lammas, the magnitude, the magnitude limitation is to just 18. But we actually find several young brown dwarfs in Lammas footprint, and we also compiled a manuscript right now, and maybe submitted recently. So if we can get if we can use the photometric data, maybe we can get a lot of low mass stars.
Yeah,
and that's very important for for study of the evolution of our galaxy.
Absolutely.
Another point is we need to use the spectral. We continually collecting the spectral of the low mass stars. So using this low mass star, the spectral, using their spectral, we can revise the theoretical model of the low mass stars. Mm-hmm. Not because they are very better than 10 years ago. They considered the people working on the the model for the low mass stars considered a lot of things better than before. But after they get all these new spectra, maybe they can find, So in the paper 2, we give some suggestions to the
Oh, nice.
In the paper. Yeah, maybe, yeah, they can, for the people who working on the model, yeah, they have some, they are the good reference for them.
Absolutely. Absolutely. Cool. Cool. Well, the future sounds bright, even if they're dim objects. Got a lot of stuff going on that'll keep you busy for a few years, and it'll keep the theorists busy improving the models yet more. So that's really awesome. Really great. So I look forward to your second paper. And Ollie, I want to thank you so much today for your time and walking us through your 2018 paper.
Thank you for interest in my paper, and thank you for having me. Yeah, thank you.
You are so welcome. All right, everyone. Thank you so much, and we will see you on the next one. Bye-bye.
Bye-bye.